Hello, today we're continuing in our series on quantum mechanics concepts, and we're going to be looking at the position and momentum operators and Heisenberg's Uncertainty Principle. You may recall from the days of the photon that we could write the state of a photon. Let's say that it was a 45-degree polarized photon, 45-degree /. We wrote that in the following way: 1 over root 2 of x plus 1 over root 2 of y. What we meant by that What we meant by that was that x was the horizontal polarizer and y was the vertical polarizer. And we now know what these two terms are. They're probability amplitudes. You need to square them if you want to find the probability. And what that says is that this squared is the probability that this state will go through the x or horizontal polarizer. And 1 over root 2 squared here is the probability that this state will go through the vertical polarizer. And that x and y are what are called basic states or basis states. They have to be a complete set. And in this case, you only need two. You either need the horizontal or the vertical, and you can express all other states as a what's called linear combination or linear superposition of them both. Well, if I write this in a generic form, I'm going to now just call the state psi. We'll find that psi becomes the generic form. It's the eigenvector, or you can call it the state, or you can call it a wave function. And we'll see why it's called a wave function a little later on. And that's going to be made up of a probability amplitude, which is the same as this 1 over root 2, times one basis vector, plus another probability amplitude, A2, times another basis vector. But so far we've only needed two basis vectors. Of course, we may now start needing more. And so you can have as many of those as you like. And that can be then more simply summarized as psi is equal to the integral over I of AI xi. Where when I is 1, this is A1 x1, that's that term. When I is 2, that's A2 x2, that's that term. But now we can have as many values as we like if we need more basis vectors. And in this video, we shall see that we need an infinite number of basis vectors. Psi can also, of course, be written as a column vector, and that would be written as A1, A2, A3, all the way down to as many as you need. And that is sometimes, confusingly, also written as psi1, psi2, psi3, and so on, where psi, which is the wave function, is also used, the sign is also used to represent the probability amplitudes. You can tell the difference because if psi is in the Dirac notation as a ket vector, then it's obviously the eigenvector. If it is in this kind of form, then it is simply representing the probability amplitudes. We also know that the probability of this state going through that polarizer is the probability amplitude squared. So more generally, we can say that the probability of going through an xi state will be equal to the associated probability amplitude, which is AI squared. I put mod squared because what that actually, of course, means, we always know whenever we do a square, we multiply the number by its complex conjugate. And the final thing to establish on this particular concept is that you'll always notice that if you get the probabilities, which of course are the probability amplitude squared, if you sum the probabilities, you always get 1, because the total probability must always sum to 1. In other words, the sum of AI star over I, the sum of all these terms must equal 1. So now I'm going to continue with some concepts that we're going to need during the course of this video. we've just shown that you can represent the wave function or the eigenvector psi as the sum over I of AI xi, where remember AI is the probability amplitudes and xi represents the basis states. So I could also have another eigenvector which we'll call phi, and that we can represent as sigma j, because this is just a summation term, and I'll distinguish it from this one by calling it j, bj xj. So now what is the bra vector of phi? Well, that is the complex conjugate of this, which means it's going to be the sum over j. To get the complex conjugate, we convert this to a bra vector, xj, and bj becomes complex conjugated. So that is the bra vector phi. So now I want to ask myself, what is this beast? Phi psi. The inner product of phi with psi is going to be, well, first we need the bra vector of phi, which is this term here, sigma j, xj, bj star, times the ket vector of psi, which is this term here. That's the sum over I, ai, xi. Now you can always bring numbers. Remember, bj and ai are the probability amplitudes. They are numbers. They may be complex numbers, but they are just numbers. And we can always bring those outside the Dirac notation. So let's just do that. So now we've got that phi psi in a product of is going to be the sum of, well, we know we've got to sum over j and I, so let's get rid of that there. Then we bring bj star and ai outside the notation. And there's no, of course, no star on ai. And that just leaves us with the inner product of xj and xi. Now, these are basis vectors. Basis vectors are, by definition, orthonormal, which means that if you do the inner product of one with another one, you get 0. We've seen this in previous videos. And if you do the inner product of one with itself, you get 1. So when j does not equal I, this term will be 0. And when j does equal I, this term will equal 1. So whenever j doesn't equal I, this term, and therefore the entire term, will be 0. So this only matters when j equals I. And when j equals I, this term becomes 1. So we can delete this term because that's now just 1. And now the summation is simply over j, because it only matters when I equals j. And so we've now found that the inner product of phi with psi is the sum of the respective probability amplitudes for phi and psi respectively. The first, of course, is complex conjugated and summed together. That in essence is what we did. If you look back at the very first video that we did, you'll find that that is in essence how we found this inner product. But now we've got a generic way of describing it. I'm continuing with basic concepts, and I want to remind you of something we developed with spin. Let's suppose we have an electron that has been prepared in the spin right direction, which means it's pointing in that direction. We showed that you could represent that as 1 over root 2 up plus 1 over root 2 down. That was actually in our last video. And once again, let me remind you, these are the probability amplitudes of being in the respective basis vector states. The basis vectors here are up and down. Those are the only two we need because those are the only two options. And if you want the probability, you have to square these terms. So if you're in the state right, the prospect of being measured up will be 1 over root 2 squared, which is a half, and the prospect of being measured spin down will be 1 over root 2 squared, a half. So if I want to ask the question, what is the prospect, what is the probability of this state being measured spin up, I simply take that term and I square it. Now let's have a look at this beast here. The inner product of up with right. Now we said what that was. It was if you prepare the electron in spin state right? That's that one. What is the prospect of measuring it as spin state up? Well, that's this. That's what we just said it was. If you prepare it in right, this is the probability amplitude, and this squared gives you the probability. So this inner product is the probability amplitude of measuring the state in spin up. And of course you have to square it if you want to find the probability. So this inner product is in essence the same as the inner product is indeed the probability amplitude for this term, and the square of the inner product is this squared, the probability of measuring an up spin. So now let's look at the more generic case of that. We're going to take our state, our eigenvector, our wave function, which is the kind of generic equivalent of the right state. And we're now going to say what we said that was. That is the sum over AI xi, where again A is the probability amplitudes and xi are the basis states. Now I want to know what is the prospect of measuring. I prepare the in state psi, and I want to know what's the probability of measuring it in a particular state xj. Well, that's going to be xj, and now instead of psi I'm simply going to put in this term here, sigma over I AI xi. That should be like that. Well, that's going to be, remember we can always pull the AI outside because that's a number, so we're going to get sigma over I AI xj xi. There is no sum over j because xj is a particular value of the basis state, a particular basis state, and I want to know what's the probability of measuring in that state. Well, now you can see that j and I, these are orthogonal, so when j does not equal I, this term is 0 and the whole thing vanishes. When j equals I, then this term becomes 1. So I can now rub that out and say that that will occur when j equals I. So you don't need the sigma term at all. It's just aj. Or if we use psi as a probability amplitude, that can sometimes be written as psi j. So in other words, what we're saying is the probability, if you prepare the particle or whatever it may be in state psi, the probability of measuring it in one of the basis states is simply equal to the probability amplitude for that state. Okay, so if you want to know what the xj, the probability amplitude of measuring it in the xj basis state, it is simply the probability amplitude. Well, we already knew that. What we want to know in this case is what is the prospect of measuring it in the second state. That's up here, that would be the second state, x2. And the answer is, that's the probability amplitude, and you square it to get the probability. But the important thing here is that the inner product of one of the basis states with the whole state psi is simply equal to the probability amplitude associated with that basis state. Let's continue with these concepts. In the first video, I introduced you to what's called the identity matrix, or the identity operator, which I said was simply a matrix which had 1 on the diagonals and 0 everywhere else. But I didn't tell you what it did. So now let me explain. If you act with the identity operator on an eigenvector, or a state, or a wave function, you will simply get back the same wave function. The identity operator I is the numerical equivalent of 1. If you multiply any number by 1, you get the number back. If you multiply a state by the identity operator, you get the same state back. Let me just demonstrate that. Let's do it in a two-dimensional case. So the identity operator in 2 dimensions will have 1 on the diagonals and 0 everywhere else. And we're going to multiply that by a state which we will simply represent as AB. And let's see what we get. We're going to get obviously another vector. 1 times A plus 0 times B is A. 0 times A plus 1 times B is B. And as you see, you simply get back the state that you started with. So you can always multiply a state by the identity operator without changing anything. And as we shall see, that is a trick we shall want to use. Let's continue with the concepts. I've already introduced you to this. The inner product of up with up. That equals 1, because up is a basis vector, and the inner product of any basis vector with itself is 1. If it had been the inner product of up with down, that would have equaled 0, because basis vectors are orthogonal. The inner product of 1 with a different one is always 0. So what then is this beast? That you'll see the vectors have simply been reversed. This produces a matrix. So let me just show how it works. Firstly, you have to put what the matrix values are. This is the ket vector of up, so that is written as 1, 0. This is the bra vector, so it is written as 1, 0. And that, instead of producing a number, which is what you would get if it were the inner product, actually now produces a 2 by 2 matrix. And the way it works is like this. You take 1 times 1 gives you the top left-hand corner. 1 times 0 gives you the top right-hand corner. 0 times 1 gives you the bottom left-hand corner, and 0 times 0 gives you the bottom right-hand corner. So it's 1 times 1 gives you that one, 1 times 0 gives you the right hand, and then we come down to the bottom. 0 times 1 gives you the bottom left, 0 times 0 gives you the bottom right. Now let's have a look at what happens if you do down, down. Well, that would be 0, 1, times 0, 1. And that's going to equal, again, another 2 by 2 matrix. 0 times 0 is 0. 0 times 1 is 0. 1 times 0 is 0. 1 times 1 is 1. Now let's add those two matrices together. And the rules are fairly simple. You just add the relevant elements in each case. So you've got 1 plus 0 is 1, 0 plus 0 is 0, 0 plus 0 is 0, 0 plus 1 is 1. And that is the identity matrix, because it's got 1s on the diagonal and 0s everywhere else. So how did we get it? We took the outer product, this is called the outer product of two basis vectors, and we took the outer product of the other two. In this case there are only 2 basis vectors, up and down. We took the outer product, and we added the 2 together, and we got the identity operator. And that suggests that if you do the sum of xi over I, you will get the identity operator I. That is to say, you take the outer products of the first of the basis vectors, and then you add the outer product of the second of the basis vectors. So in this case you would only need to go from I equals 1 to 2, and you add them together, you get the identity operator. And the real question is, does that work for any value of I? Well, that's what we're about to test. So I am postulating that the sum over I of xi equals the identity operator. So let's try it. We know, because we just showed it a few moments ago, that the identity operator acting on a matrix, or acting on a ket vector, eigenvector, state, wave function, simply gives you back that self-same wave function. So we know that's the case. So now let's have a look at this term here and see what we get. That's going to be sigma I, xi, xi, and let's act now. That is, I assert that is the identity operator, but I've got to demonstrate that. So let's act that identity operator on psi. And of course, if that is true, if that is the identity operator acting on psi, I should get psi back. But let's see what we get. So I can rewrite this as the sum over I of xi, xi. I've not changed anything. But for psi, I'm now going to write what we have written before, which is the sum over j of the probability amplitudes times the basis states. We've shown that in this very video. So now you can always pull out the numbers. They don't have to stay inside the notation. So we're going to get the sum over I and j, that's I and j. We'll pull out aj, because we can take that outside, and that's going to leave us with xi, xi, that's those two terms, and now xj. Well, xi, xj, again, is that self-same issue we've had so many times before. If I does not equal j, this term becomes 0, and therefore the whole thing becomes 0. And if I does equal xj, then it simply becomes 1. So we can take that out because it's 1. And now we only need to sum over j, because it only matters when I equals j. And now we've shown that this term here is equal to the sum of over j of aj xj. But that's psi. That's this, which is this. And so we've shown that the sum of the outer products of the basis vectors is one and the same as the identity operator. Just a couple more of the concepts that we need to get out of the way before we can start on the main theme. I now write up what should be now a very familiar equation. This says that if you take a Hermitian operator and act on an eigenvector, you get the same eigenvector but with an eigenvalue. Or in physics terms, what we're saying is that the measurable, which is represented by the operator, acting on a state, will pick out a particular state represented by the eigenvalue. Now, this is to try and show you how you can define whether an operator is Hermitian. Let me write this beast. So I've simply taken this here and done the inner product with psi, the same value of psi as here. That's going to equal psi. Now h acting on psi, if it is Hermitian, if and only if it's Hermitian, will give you lambda psi. Right, that's if it's Hermitian, it won't otherwise. But lambda is a real number, so that can come outside, and that's going to give you lambda psi psi. But the inner product of psi with psi is 1, so that just gives you lambda. Now that only arises if h is Hermitian. So what we can say is that if you're testing to see whether h is Hermitian, if you put it in the middle of two eigenvectors, if h is Hermitian, you will end up with a real number, but you won't otherwise. Here's a second test for Hermitian operators. Let's consider this beast here. Phi h psi. And now I want to complex conjugate it. So it's just phi h psi complex conjugated. Now what is phi h psi complex conjugated? Well, if you complex conjugate the psi, that's a ket vector, it becomes a bra vector. If you complex conjugate the bra vector phi, it becomes a ket vector. And if you complex conjugate h, which is an operator, then you have to dagger it. That is to say, it is the transposed complex conjugate of H. But if H is Hermitian, then the test or the definition of whether an operator is Hermitian is that the operator is equal to its own transposed complex conjugate. So if that's the case, if H is Hermitian, then H equals H dagger. And now you can see what you've got. You've got that phi H psi, all complex conjugated, is equal to psi H phi. And that was only true if H is Hermitian. So that's another test for whether or not H is a Hermitian operator. So now we're at a stage where we can think about the position operator, which we're going to call X. So it's going to be a matrix, it's a position operator, it's obviously a Hermitian operator, it's going to act on a state, and it's going to give us back the same state multiplied by an eigenvalue. And what eigenvalue would we like? Well, we would actually rather like to know where the particle is. That's why it's called a position operator. So it would be handy if the position operator returned an eigenvalue which was the actual position of the particle. So we have to ask ourselves, where is the particle? Well, if we don't put any limits on it, it could be anywhere. Anywhere in the universe, which is rather a large place to look. So we tend to restrict this by making it a one-dimensional problem. So here is our one-dimensional universe, which of course stretches for practical purposes from -infinity to infinity, which is still a long way. And what we're saying is the particle can be anywhere on that line. So every single point, and there's a continuum of points, every single point on this line is a possible location for the particle. Which means that every single point on that line represents a basis state. They are all orthogonal in the sense that if the particle is at one point, it definitely isn't at another. So you've got an infinity of basis states. Every single point on this line is a possible location for the particle. So every single one of them represents a basis state. And there must be a probability of the particle being at any one of those points. And the probability amplitude, which we will call psi, the probability amplitude for each point will be represented by some kind of curve. That is to say that the probability amplitude for a particle being at this point is given by its value there. So just as when we just had when we were talking about spin or when we were talking about polarisation, we only had two possible states. And for each state, two possible states, and for each state there was a probability amplitude. Now we're saying we've got an infinite number of states, and for each possible value we've got an associated possible probability amplitude. And of course, if you want to know what the probability is of finding a particle at this point, then you need to take psi star psi, essentially the square of this term, which means the probability amplitude multiplied by its complex conjugate. Now, in reality, if you are faced with this problem where there is a probability amplitude stretching from -infinity to infinity, then the problem is nigh on insoluble. Because what you're effectively saying is that there is a probability of finding the particle right on the other side of the universe. There's a probability of finding the electron somewhere 13.7 billion light years away. And if that's the case, the prospect of you finding it is vanishingly small. So for all practical purposes, what we actually do, if we create an electron in the lab and we say, where is it? We say, we know that it's not on Mars, and we know that it's not on Venus, so the probability of it being at these extreme lengths, the probability amplitude and the probability is 0. And then you say that only within a certain defined range, which we'll call L, only within that range is it likely that the particle will be found. And if we don't know where it might be found, and it's just as likely to be found in one place as another, then of course the probability amplitude will be the same for all positions. So what we're effectively saying is that once you get to beyond a certain point, then the probability of the electron being there, or particle being there, is zero. Only within certain constraints can we be pretty confident, indeed very confident. If you create the electron in the lab, then it isn't on Mars. Where it is in the lab, you don't necessarily know, but you know that there are limits beyond which it's not going to be found. But you don't know where in the lab, and it could be equally anywhere, so you give it the same probability. Unless you've got, of course, reason to believe that it's more likely to be in one place than another, in which case you might have a curve. So this represents the probability amplitude for finding the particle at any point. What is the probability amplitude of finding it at that point? Answer, that value. And clearly what you've got to do is to do psi star psi to find the probability of finding the particle at any point. So what is the probability of finding the particle at that point? It's going to be psi star psi, which is that value there. There's something else you can say, and that is that the area under this curve, under the probability curve, that area must equal 1. Because if you look at it, that is the sum of the probabilities for all possibilities. And since the particle must be somewhere, and it can't be anywhere else, once you've located it here, it can't be anywhere else, the probability of finding it must be 1. And so the sum of all the probabilities for all the different points must add up to 1. So how are you going to find it? What is the piece of equipment that represents the position operator? Well, we used to use a piece of equipment which looked something like this. For spin, for example, we measured the spin up or down according to the arrow, and we had two lights, a red light and a green light. And if the red light came on, that meant the spin was up. And if the green light came on, that meant the spin was down, according to the direction of the arrow. And of course, we could always twist the equipment. But for each measurement, we only got one of two results. Well, that's going to be of no use at all to us here, because we haven't got only one of two results. We've got one of essentially an infinite number of continuous results along this line. So that equipment's no good. But I'll tell you what, let's have something rather akin to the piece of equipment that people who use metal detectors have. You know, these are the people you see walking along the beach after a warm sunny day when lots of holidaymakers have been sunbathing on the beach, and the people come along with their metal detectors in the hope of finding money buried in the sand. Well, we're going to have a similar sort of thing, only except instead of a metal detector, we're going to have an electron detector. And we walk along this line here, and we have a ruler with graduated points. This is x equals 0, and then you go along with varying values of x. So you take your electron detector and you walk along this line until it goes ping. And when it goes ping, if it goes ping there, that means that's where the electron is. You found it. And you measure it against the ruler. And that, of course, gives you your value of x. So we go along with our electron detector until it goes ping, that's where it is, and we measure off the value of x on the scale. And that's essentially what this is. X is essentially our electron detector. Psi is our set of states. It is the linear superposition of all these points in the continuum. And x is the actual value which we get out of measuring where the electron is. And that is essentially the position operator. The position operator gives you the eigenvalue of x, which is the actual location or position of the electron. Now, the fact that the states were continuous, remember that when we had the line going from -infinity to infinity, we said that the electron could be found at any position, and every single one of those continuous positions could be regarded as a possible state. what we're now going to have to do is to revise some of our formalism, because we used to say that the wave function, the eigenvector, which is the linear superposition of all states, could be written as the sum over I of AI xi. But that was true when these states were discrete. They were up and down, or they were polarisation horizontal or polarisation vertical. But now these states are continuous. And whenever you have a continuous system, you have to change the summation term to an integral term. And unless you know otherwise, you usually have to integrate from minus infinity to infinity. It was along the x-axis, so this dx essentially replaces the discrete basis vectors, and now you simply take ai. So you integrate for all values of ai, which can also be represented, of course, I can change ai to psi I, if I want to call the probability amplitudes psi I. And remember, we said that along this line, this is essentially the x-axis with all the possible values of x that the electron could be at. And this is the psi axis, and we said, you know, there was a probability amplitude associated with each point on the x-axis. And what this integral does is it integrates right the way through for all values of psi according to the x-axis. We're also going to need to do an adjustment to this term, which you recall we worked out earlier in this very video as being the sum over j of phi star j and psi j. Now, if we are talking about a continuum, as we were, then again you're going to have to replace the sum term by an integral term from minus infinity to infinity, unless you know that you don't need that, dx, and now you're going to need phi star at all values of x and psi at all values of x. So you're simply taking the integral of phi at all values of x times psi at all values of x. And now, before we get on to the momentum operator, I just need to make sure you understand the concept of integration by parts. If you have two functions, u and v, which are both functions of x, and you want to know what is the differential with respect to x of the product of uv, then that's called differentiation by parts. And the way it works is you take the differential of one with the other standing by, and you add to it the first, and then you differentiate the second. Now, I can rewrite that as u dv by dx is equal to this term here, d by dx uv, minus this term here, du by dx times v. Now I can integrate. And normally, of course, you integrate from minus infinity to infinity, unless you know otherwise. But I want to draw your attention to this term here. This is the integral of a differential. Well, if you integrate from minus infinity to infinity of a differential, that is simply the original term evaluated from minus infinity to infinity. But in the work that we're going to do, I'm going to have u equal to psi and v will equal psi star. So I'm preparing the ground for this. And we've already said that at infinity, psi and psi star will equal 0, because if you've still got a probability amplitude of finding a particle at infinity, you're sunk. You will always have to constrain where that particle is, otherwise you can't do the work. So u and v at infinity are both going to have values of 0. So when you evaluate this at minus infinity and infinity, those terms are both going to be 0. So this term just disappears. It only disappears under the express, as I've said, under the express conditions that u and v at infinity are 0. And now you'll notice an interesting thing. that the integral of u dv by dx is equal to the integral of du by dx times v, but with a minus sign. So wherever you have this kind of form, you can change it to that form, but with a minus sign. So now we are ready to look at the momentum operator. But before we do, let me write down an operator. That's an operator. It can operate on psi by simply differentiating it with respect to x. Now I can tell you that that is not Hermitian. I won't waste time proving that it's not. I'll simply tell you what you need to do to make it Hermitian and then show that it is. So you make it Hermitian simply by multiplying it by minus I. That is now Hermitian, and you'll want me to show you why. Well, you'll remember that earlier in this video we said that if an operator is Hermitian, then psi h phi is going to equal phi h psi all complex conjugated. That was earlier in this video. We said that that was the test that an operator h, let's put hats on it so you can see that it's an operator h, is Hermitian. Well, let's write that out. That means that we've got, if h is minus I d by dx, right, that's the operator acting on psi, then this becomes psi and then minus I d phi by dx, right, because we've operated on phi and that's the operator. And that we are alleging, so I better put a question mark, is this true, becomes phi minus I d psi by dx, all complex conjugated. Now you'll recall that we showed earlier in this video that you could take an inner product of two vectors and express it in terms of an integral. Furthermore, we can take the minus i's on the outside. So we're going to get minus I times the integral dx of psi star times d phi by dx. Right, that was just the form of the inner product. And that's going to be equal, question mark, to take the minus I on the outside, minus I times the integral dx of phi star d psi by dx, all complex conjugated. But now I'm going to use the integration by parts trick that we just developed, which says that when you've got the integral of this term with this term, you can change it to be d phi star by dx multiplied by psi, but you have to change the sign. So this becomes plus I, all complex conjugated, dx, but now we just have the differential on the other term, so it's going to be d phi star dx times psi, all complex conjugated. And now we have to ask ourselves, is this term the complex conjugate of this term? And you can see that it is. Because to complex conjugate, firstly you have to change the sign of the imaginary term, and minus has become plus, so that's okay. To complex conjugate you have to swap these two terms and then complex conjugate both. So if you swap this term psi star, it becomes just psi. And if you swap this term and complex conjugate it, it becomes d phi star by dx. So we've shown that this is the complex conjugate of this, and consequently this term here is Hermitian. So now we have an operator. I don't know what sort of operator it is. I'm going to call it k, and it is equal to I d by dx, sorry, minus I d by dx, which we've just shown is Hermitian. So it's definitely an operator. So we can definitely use it in the form that the operator acting on a state or wave function, psi, is going to equal a eigenvalue, which I'm using k again, psi. And you can tell the difference because the eigenvalue is k, the eigenvector is k hat. So that means that k, which is minus I d by dx, acting on psi, is going to equal k psi, because I've just replaced the operator by what it actually is. If I multiply through by plus I, then plus I times minus I is minus I squared, which is simply plus 1. So now I get d psi by dx is equal to ik psi. And that has a solution. Whenever you have anything, the differential of a term is equal to a constant times that term. The solution to that term is that psi is equal to e to the ikx. And if you just want to check, if you do the differentiation of this, differentiate this with respect to x to get this term here, you bring the ik down on the outside, so you get ik times e to the ikx, but e to the ikx is psi. So there's the demonstration that that's the term. But we should recognise what e to the ikx is. We've come across this term many times before in the past when we've been dealing with waves. E to the ikx is simply cosine of kx plus I sine kx. That is its identity. So now we know what psi is. It is, in the real terms, an oscillating cosine wave, and there's an associated imaginary sine wave. And that, of course, is the reason why this is called a wave function, because in this scenario it is actually a cosine wave. And now we recognise what this k term is, because in this context, k, of course, is simply the wave number, which is 2 pi over lambda. I draw your attention also to what I've called the de Broglie formula, P equals h over lambda. It strictly ought to be called, I suppose, the Einstein formula, because it was Einstein who said that if you're talking about photons, the momentum of a photon is equal to Planck's constant divided by the wavelength of the light. It was de Broglie who got a PhD and a Nobel Prize for rearranging this formula to say lambda equals h over p. Now, on its own, that is not particularly clever. Even I could do that. But de Broglie's genius was to realise that whilst Einstein had developed this formula for photons, this formula could be used for electrons. And you knew what the momentum of an electron is. Momentum is mass times velocity. So if you knew the mass and the velocity of the electron, de Broglie postulated that that would mean that the electron would have a wavelength. And that would mean that the electron was not only a particle, but also a wave. And that concept was really the birth of quantum mechanics. But let's not get carried away with that. Let's get back to the problem. That means that k is 2 pi over lambda, but lambda is h over p. And now we can rewrite h over 2 pi as h bar, where h bar is Planck's shortened constant. It's h over 2 pi. And so now we know what k is. It is actually momentum divided by h bar. Consequently, psi, our wave function, is equal to this term here, which is e to the I. Now, instead of k, I'm just going to put p over h bar. P over h bar times x. So we now have a wave function which involves momentum. So there it is. The wave function is e to the ipx over h bar. So let's think, what is the differential of that wave function? D psi by dx is going to be, well, you just bring the ip over h bar down on the outside, and that is going to multiply by this term, which is simply psi. And now I'm going to multiply both sides by h over I. So I'm going to get h over I times d psi by dx. If I multiply h over I, that just goes, and I'm simply left with p, the momentum, times psi. If I multiply top and bottom by minus I, then the bottom becomes minus I squared, which is 1, so that goes. And that, incidentally, should be h bar. because that's h bar there. So I've got minus I h bar d psi by dx equals p psi. And if I take this term here, minus I h bar d by dx, and call that p hat, acting on psi, that's going to give me p psi, where p hat was minus I h bar d by dx. Now we already showed that minus I d by dx was Hermitian. All we've done is multiply it by a constant h bar. So this is also Hermitian, which means it's an operator. And when the operator acts on psi, it gives the same eigenvalue psi, but multiplied by p, which is the momentum. So p hat, this term here, is simply the momentum operator, which delivers the momentum. So now I want to ask the question, can we measure two observables at once? In particular, I'm going to ask, can we measure position and momentum at the same time? And this, of course, is going to lead to Heisenberg's Uncertainty Principle. But let's get there in stages. Suppose I have a measurable, m1, which acts on a state A to give me some kind of eigenvalue alpha, of course, on the same state A. Now, if I want to do a different measurement at the same time, I'm going to need a different operator. Let's call it m2. These are operators. And that will need to act on the same state to produce a different eigenvalue, beta, acting on A. Now, it has to act on the same state because we're doing this simultaneously. If the system is in a state, that's the state it's in. So you have to measure that state. So the state will be the same if you're doing it simultaneously. Now I want to do two calculations side by side. On this side I'm going to do M1, M2A, and on this side I'm going to do M2, M1A. What this means is you act M2 on A, which is this here, and then you act on with M1 on the product you get as a result of this. So let's do it. M1, what is M2 on A? That's beta A. What about here? This is M2. What is M1 acting on A? That's just alpha A. These are numbers. In fact, they are real numbers because these are eigenvalues. So we can pull those outside and we now get beta M1 on A, and here we get alpha M2 on A, which is going to be beta times, now what is M1 on A? Well, that's just alpha A. Here we've got alpha. What is M2 on A? That is beta A. These are numbers. So beta times alpha equals alpha times beta. 3 times 2 is the same as 2 times 3. So these two are equal, which means those two are equal. So if you like, you could write this as M1, M2 minus M2, M1 acting on A equals 0. Because those two are equal, so if you take one from the other, sorry, that shouldn't be a minus there, it's minus M2, M1 acting on A is 0. This term minus this term, since they're equal, that will be 0. And this M1, M2 minus M2, M1 is called a commutator, and it's written M1, comma, M2. Whenever the commutator is written in square brackets with a comma, that literally means this. It's the shorthand way of writing M1, M2 minus M2, M1. And that obviously has got to equal 0 because state A doesn't equal 0, and since the whole product must be 0, it must be this term which equals 0. Now remember, if these were numbers, it would always be 0. 3 times 2 minus 2 times 3 would always be 0. But these are not numbers, they are operators, and they do not always equal 0. But if you're going to measure two things at the same time, then the commutator must equal 0, which is another way of saying that the two operators must both be able to act simultaneously on the same state. And that means that this state must simultaneously be an eigenvector of M1 and an eigenvector of M2. And if M1 and M2 do not have common eigenvectors, you cannot measure them at the same time, and the commutator will not be zero. So the question reduces to, is the commutator of the operators x and p zero? I put a question mark because that's what we've got to establish. If it is, then we can measure position and momentum at the same time. If it isn't, then we can't. So let's just think about what this was. We remember that was just xp minus px. That's what the commutator is. And we've got to work out what that is. Well, x, remember, would simply return the value x. That is the actual position of the particle, multiplied by the operator, which we just showed was minus I h bar d by dx. And these are operators. Operators operate on something, so we better operate on something. We'll just operate on psi, whatever psi might happen to be. And that's going to be, and then you're going to do minus, again you've got minus I h bar d by dx times x, and operating on, of course, psi. X just gives you back the number x. Well, this is just a number, so we can stick this anywhere we like. So this is going to be minus I h bar x d psi by dx. That's just this term here. Minus, now we've got the differentiation of a product, x and psi. So we better do, we've got a minus times a minus, so that's a plus. So we can take those two minuses together. And now we've got, in fact, I can put the IH bar outside. So I've got plus IH bar, and now I've got the differential of a product. So that's going to be dx by dx times psi plus x d psi by dx. When you do the differentiation of a product, you differentiate one term with the other standing by, and then you do that term and you differentiate the second. Now, we've got a minus IH bar x d psi by dx, and we've got a plus IH bar x d psi by dx, so those two terms disappear. Dx by dx is simply 1, so that disappears. And what I'm left with is IH bar psi. That times that. Psi was the state that we acted on. So in fact, xp minus px is simply plus IH bar. xp minus px acting on psi gave us IH bar psi, so xp minus px is IH bar, which significantly does not equal 0. And that's the reason that you cannot measure x and p at the same time. And that essentially is Heisenberg's uncertainty principle. It has nothing to do with the difficulty of doing the measurement, though that is a problem. It has nothing to do with the sensitivity of the equipment, though that is a problem. It has nothing to do with the fact that when you measure something, you interfere with the thing you're measuring, though that is a problem. This is something much more fundamental than all of those practical difficulties. This says you cannot measure x and p at the same time because the position operator and the momentum operator do not have common eigenvectors, and they would need to have common eigenvectors to measure them simultaneously. So no amount of improvement in our technique will ever get us to a situation where we can definitely measure position and definitely measure momentum at the same time. As a ket vector, then it's obviously the eigenvector. If it is in this kind of form, then it is simply representing the probability amplitudes. We also know that the probability of this state going through that polarizer is the probability amplitude squared. So more generally, we can say that the probability of going through an xi state will be equal to the associated probability amplitude, which is AI squared. I put mod squared because what that actually, of course, means, we always know whenever we do a square, we multiply the number by its complex conjugate. And the final thing to establish on this particular concept is that you'll always notice that if you get the probabilities, which of course are the probability amplitude squared, if you sum the probabilities, you always get 1, because the total probability must always sum to 1. In other words, the sum of AI star over I, the sum of all these terms must equal 1. So now I'm going to continue with some concepts that we're going to need during the course of this video. We've just shown that you can represent the wave function, or the eigenvector psi, as the sum over I of AI xi, where, remember, AI is the probability amplitudes and xi represents the basis states. So I could also have another eigenvector, which we'll call phi, and that we can represent as sigma j, because this is just a summation term, and I'll distinguish it from this one by calling it j, bj xj. So now what is the bra vector of phi? Well, that is the complex conjugate of this, which means it's going to be the sum over j. To get the complex conjugate, we convert this to a bra vector, xj, and bj becomes complex conjugated. So that is the bra vector phi. So now I want to ask myself, what is this beast? Phi psi. The inner product of phi with psi is going to be, well, first we need the bra vector of phi, which is this term here, sigma j, xj, bj star, times the ket vector of psi, which is this term here. That's the sum over I, ai, xi. Now you can always bring numbers. Remember, bj and ai are the probability amplitudes. They are numbers. They may be complex numbers, but they are just numbers. And we can always bring those outside the Dirac notation. So let's just do that. So now we've got that phi psi in a product of is going to be the sum of, well, we know we've got to sum over j and I, so let's get rid of that there. Then we bring bj star and ai outside the notation. And there's of course, no star on A. Hello, today we're continuing in our series on quantum mechanics concepts, and we're going to be looking at the position and momentum operators and Heisenberg's uncertainty principle. You may recall from the days of the photon that we could write the state of a photon. Let's say that it was a 45-degree polarized photon, 45-degree /. We wrote that in the following way: 1 over root 2 of x plus 1 over root 2 of y. What we meant by that, what we meant by that was that x was the horizontal polarizer and y was the vertical polarizer. And we now know what these two terms are. They're probability amplitudes. You need to square them if you want to find the probability. And what that says is that this squared is the probability that this state will go through the x, or horizontal polarizer, and 1 over root 2 squared here is the probability that this state will go through the vertical polarizer, and that x and y are what are called basic states, or basis states. They have to be a complete set, and in this case you only need two. You either need the horizontal or the vertical, and you can express all other states as a what's called linear combination or linear superposition of them both. Well, if I write this in a generic form, I'm going to now just call the state psi. We'll find that psi becomes the generic form It's the eigenvector, or you can call it the state, or you can call it a wave function, and we'll see why it's called a wave function a little later on. And that's going to be made up of a probability amplitude, which is the same as this 1 over root 2, times one basis vector, plus another probability amplitude, A2, times another basis vector. But so far we've only needed 2 basis vectors. Of course, we may now start needing more. And so you can have as many of those as you like. And that can be then more simply summarised as psi is equal to the integral over I of AI xi. Where when I is 1, this is A1 x1, that's that term. When I is 2, that's A2 x2, that's that term. But now we can have as many values as we like if we need more basis vectors. And in this video, we shall see that we need an infinite number of basis vectors. Psi can also, of course, be written as a column vector, and that would be written as A1, A2, A3, all the way down to as many as you need. And that is sometimes, confusingly, also written as psi1, psi2, psi3, and so on, where psi, which is the wave function, is also used, the sign is also used to represent the probability amplitudes. You can tell the difference because if psi is in the Dirac notation, I, and that just leaves us with the inner product of xj and xi. Now, these are basis vectors. Basis vectors are by definition orthonormal, which means that if you do the inner product of one with another one, you get 0. We've seen this in previous videos. And if you do the inner product of one with itself, you get 1. So when j does not equal I, this term will be 0. And when j does equal I, this term will equal 1. So whenever j doesn't equal I, this term, and therefore the entire term, will be 0. So this only matters when j equals I. And when j equals I, this term becomes 1. So we can delete this term because that's now just 1. And now the summation is simply over j, because it only matters when I equals j. And so we've now found that the inner product of phi with psi is the sum of the respective probability amplitudes for phi and psi respectively. The first, of course, is complex conjugated and summed together. That in essence is what we did. If you look back at the very first video that we did, you'll find that that is in essence how we found this inner product. But now we've got a generic way of describing it. I'm continuing with basic concepts, and I want to remind you of something we developed with spin. Let's suppose we have an electron that has been prepared in the